Good. Thank you very much. Looking forward to kind of doing a broad brush here, getting in a little bit of testing theory, how energy waves propagate, what information we collect from that, talk about some equipment, some applications, and save some time for some questions at the end. So energy wave propagation, what do we need to glean some of the information? It's velocity information. We're recording energy waves, compressional wave velocity, shear wave velocity, and how that energy wave gets refracted and reflected based on different anomalies. Generally, if it's a faster material, faster energy wave, it's going to be a stronger material. Now, we can be impacting a element like a concrete pile, concrete member, or we can be impacting the ground and tracking how these energy waves propagate through different material or rock, and then get the strength and the depths of those. So as a close-up, you might want to picture dropping a pebble in a pond. The rings radiate out. We're recording the velocity of those energy waves relative to the energy source and the sensors that are placed at known distances. We're recording a surface wave that travels along the face of concrete or the pile. We're also recording a reflected wave, kind of the echo that goes down. So we're getting the surface reading, and then we're getting a vertical component simultaneously. The data that we're looking for are the first arrivals after that dashed vertical red line. Those are the second and tertiary arrivals. There's energy bouncing all over the place, but the first arrival on our channel 1, channel 2, or 3 gives us the information. The compressional wave arrives first, has its own little fingerprint, shear wave comes in second, and then there's a double hitch or Raleigh wave, which also provides information. So as far as testing concrete, there's a picture of the impact echo pulse velocity. I'll get into those two test methods on the next slide. Energy source is on the right. It's an air gun hooked up to a tank of nitrogen, fires a special steel bearing. Every time we pull the trigger, we're initiating a repeatable energy source. When you swing a hammer, it's not always the same energy, but this is much more accurate and very repeatable. So we're collecting data according to two ASTM procedures. Pulse velocity, that's the surface wave that travels along. And then the other one is the impact echo. Both of these are in the concrete side of the ASTM spec. So on the impact echo, the energy wave gets trapped between boundaries, and it just oscillates back and forth at a certain frequency and amplitude. And we can get the thickness of that concrete. And if there is some delaminations between the rebar and concrete, that thickness frequency is going to change. So it's a definitive way to quantify where there is debonding or delaminations within concrete. Over the 30 years that we've been testing concrete, we've developed a very accurate curve to equate the velocity to compression strength of concrete. It's usually within about 500 psi. Often there's some skepticism out there where I'll identify where our values are. We'll take a core, break the core, it hits within 500 psi. That's a great calibration opportunity. Now let's think about that. You take the core out of the element, send it to a lab, and break it. When I'm testing, I'm actually getting in situ compressive strength. So it's representative of the internal stresses that may be on the beam or the column or the slab. So I'd argue my numbers are maybe even a little more accurate than a lab break miles away. The picture before was a surface testing. Assuming we have access to all sides of our particular member that we're testing, we can do cross testing, many crossing wave paths, generate a tomographic image, and then slice it. This is very similar to what the medical community does with ultrasound testing of our heart or our brain or our spine or kidney or what have you. So again, access to both sides. Where this often plays very important, valuable information is even with new concrete, consolidation issues, honeycombing issues, being able to quantify the extent of the anomaly and how far does that go back in. So don't underestimate the value of proper concrete placements, or even horizontal cold joint, waiting for a truck. Is the top concrete bonded to the lower section of concrete? If the energy wave crosses over that, it is. If the energy wave does not get picked up in the other channels, the other sensors, unfortunately, that's acting as two individual concrete. So this is an application I've been doing more and more evaluation of fresh concrete, but it's also very applicable for evaluating existing concrete, the condition assessment. On this particular bridge foundation, the perimeter surface concrete, less than 1,000 PSI. There was some failed shotcrete, cover's gone, rebar's rusting away. The core strength, now we've got the energy source on the left and the sensor on the right. So we're testing right through that concrete. Surface, terrible. Core strength, 6,000 PSI. No need to demo that particular bridge pier. Now the deck on this bridge was coming off, but this was conclusive data that we were able to provide to salvage the 4 piers on here. They were on piles, there was scour protection. A great example of preserving concrete, not adding it to the landfill and not honestly spending more carbon to make more concrete. Another application was a closure pour on a concrete pier, precast below the 2 man baskets, precast above. There was a closure pour. There was some concern about consolidation. On the lower left there, about 3 clicks over and 4 clicks down, it's not blue. The blue's about 7,000 PSI. So there was some change in the consolidation and the ultimate strength of that concrete. Now, it was very isolated, and it was only in slice E we had access to both sides of that closure pour, and provided this information to the engineer and the owner. They could decide the significance of this anomaly, but now it wasn't red, it wasn't a coffee cup or a paper bag, but it wasn't 7,000 PSI like it was supposed to be, but it was very isolated. When looking at depths of crack, we can also use the geometry to identify the relative depth. We would move the energy source away from the crack, or perhaps move the sensors away from the crack, and eventually we'll have the geometry that breaks through and we pick it up on the other side. Now, we generally provide the crack depths as kind of superficial crack depths, 0 to 3 inches, moderate 3 to 6, or greater than 6. But it's better information than just looking at a crack and wondering how deep does that go. Now, in terms of when there's borings available and looking at soil strengths and rock strengths, we're doing the same thing, but we're sending the energy from within the boring and picking that up within another boring. Also, it's important on deep borings to have the inclinometer to know if there's changes when the borings were installed. So very valuable here. And it's just a series. We need to know what depths the energy source goes from. We're transmitting from boring on the left to the boring on the right. This happened to be a triangular pattern. But by these crossing wave paths through the soil, we can identify the strength of that. So I'll get into a little bit more of the testing equipment. We just touched base on how these energy waves propagate. The pulse velocity, the impact echo, I think we've done that justice. That's mechanical energy. Ground penetrating radar, we'll talk a little bit about that, and touch base on seismic refraction surveys. So GPR is electromagnetic energy, and the takeaway for everybody is there's different frequencies for GPR. Some of the high frequency works in concrete, low frequency works in soils for locating utilities, and it's the electromagnetic energy that gets reflected off a conductive material. Rebar is very conductive. Salt water is very conductive. And we're trying to measure the electrical density, if you will, of the soil or the material that we're testing. Some different examples of radar equipment. On the left is the Mini XT. It's a high frequency 2700 megahertz. The self-contained Mini in the middle, about the size of an iron, and it's great for locating rebar, pre-stressing strands. The antenna gets a little bit bigger on the 900 megahertz on the right, evaluating some bridge for load ratings. What's the asphalt cover? What's the concrete deck thickness? What's the soil that might be adjacent to that? That antenna gets even bigger, a 400 megahertz. Come back here. 400 megahertz. On the left for sinkholes, leaks, and earthen dams. Again, water is conductive. Where we have the water, we're going to pick up the leaks, quantify them. And the 200 megahertz is probably at the low end of infrastructure GPR assessments. But there's a big range and that antenna, again, gets much bigger. It sends and receives the electromagnetic energy. It's a shielded antenna. So what kind of data do we get? On the left, each one of those parabolas is an individual rebar, and we know what the cover distance is from the concrete. But past station 78 is kind of washed out. Some moisture in there, there's some air void. Something's changing the signal down there, and we can identify that. On the right, there's an overlay, a concrete slab, and a void underneath the concrete slab. This was from a 900 megahertz. Often you might need to stack different antennas over the same area to get different depths, and then you put it all together. Quick review, the takeaway, different frequency. It's the same thing that tracks the planes and tracks the thunderstorms. It's just different frequency and wavelength. So that's the takeaway. High frequency, rebar, pre-stressing strands, low frequency voids under slabs, utility locations, that sort of thing. Seismic refraction. This is a bigger bang than a BB gun, and it's a black powder energy source and longer arrays, 100, 200, 400 foot arrays with hydrophones or geophones, but we're still measuring the velocity of these shear wave and compressional waves in the soil to get the depth and the relative strength. Today, rock strength can be quantified from shear wave velocity. Caterpillar does it all the time. The 3-to-1 ratio, if we're going down 100 feet, we ought to have 300 feet of surface sensors to collect that data. If we're only going down 30 feet, maybe we can get away with a 100-foot refraction line. And great for bridge alignments, scour evaluations if an abutment's on rock, and we know that. That's a good way to quantify the vulnerability. Roadway alignments, pipeline construction. Maybe you just need to know that the rock is 6 feet or deeper, so you're not going to hit it when you're putting a fiber optic line in or a water line. So other valuable information there. We need an energy source. We can hit the bedrock, hit a plate. We can have a size gun with a little blasting mat down in the water, or much larger ones, an air gun or even explosives. The data that's collected is from a 12 or 24 channel seismograph. We've got cables, hydrophones, geophones collecting this data. If there's a borehole, we've got energy sources that are deployed from the borehole, or sensors that collect the energy results from the borehole. So a couple more applications here. Bridge alignment. The hypotenuse on the left image was the proposed alignment, and in 2 days we were able to quantify 1,400 feet of bedrock profile elevations. Would take an awful lot more time with borings, and with knee-deep water would be a very big challenge, but very, very successful when it was done early on in the design process. Pile testing for lengths, okay? We record the velocity in the pile and then record the two-way travel time. We have velocity, we have time. Easy to calculate the length. Works on timber piles, works on concrete piles, works on all types of steel piles. And if there's an anomaly in a concrete pile, drilled shaft, and we have access to the top of the pile, we can possibly quantify the extent of that anomaly, the northern part, southern part, east or west, whatever quadrant it might be in. All types of piles, concrete, timber, steel, just a variety, a mishmash of piles in this image here. Here we're testing on the left concrete pile, drilled shaft there, a timber pile. We've got the sensors in a ratchet strap, and there's a series of sensors at known distances. Sheet pile, concrete filled pipe piles. Sometimes the piles are not accessible. Maybe there's a jacket on the piles and we can't test through the jacket. Our equipment is waterproof. We put it in the hands of divers all the time. The trick with piles, if I'm at the middle of the pile and I hit it, I'm going to get an energy wave that goes up and down. I'm going to get one that goes down and comes back up. Might not be able to differentiate which one's which. So I'll move higher than the midpoint, or I'll move lower than the midpoint, which might require the divers to do that. Then we can differentiate the one that we're not interested in. Back to a borehole. If we have a borehole with a casing and we can impact a part of the structure on the right, we can have a series of sensors in the borehole and then tell, without excavation or access to the pile, what the depth of that pile might be. But you need a borehole, and it ought to be within about probably 5 feet, maybe 6 feet, 2 meters or so. Crosshole applications for when there's multiple boreholes, foundations, bridge foundations, bearing capacity, All very, very valuable. Crosshole, when there's direct wave data, we're trying to record the data, we're recording the velocity, interpreting that for what the strengths are. Saw this one before, again, energy sources in one boring, picking up where the sensors are in the other. When we have this information, we can do crosshole tomography and slice it like we did on the other one, and generate the images to quantify all of that. If we just have one borehole, we can impact the surface of the ground and walk that away from the boring and get information on the ground there as well. Other applications is just a broad brush. I know I'm running late on time here, but dams, pipes, buildings, utility location, post-tension tendons, supposed to be grouted, same thing. We can tell when there's voids in there, water voids, air voids, or grout that just never set up based on how the energy waves propagate through that. External tendons, internal tendons, corrosion can happen fast. Those pictures on the left are all voids. That should be a full tendon duct. It's not. Strands are corroding, and it's going to fail. We've partnered with ASI Marine, and we can do concrete testing underwater. We've installed this on an ROV. Some places you just don't put divers, and I don't believe anybody can do concrete integrity testing from an underwater ROV. Last slide here. Microphone technology. We've got a research grant with the Federal Railroad Administration to locate locate cracks in concrete ties. So microphone technology. We don't have to have contact sensors on the concrete. I'll take any questions. Jack, if we're okay on time, let me know.
Actually, we're out of time. I'm going to take one quick question if somebody's got it.
Any questions out there? Thank you. I'll be around here if there's any questions. Thank you very much, everybody.